the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is, I don't know which number it is in a series on an introduction to linear algebra, but it's one of them, right? It's probably the 8th or the 9th video in the series. You should have already reviewed linear systems and kind of the definitions behind linear systems, and then a review of matrices, the size of a matrix, what a coefficient matrix is, and what an augmented matrix is. After going through all of that, we're going to review a little bit of old school algebra in a more theoretical fashion. Now, this, honestly, I've gone back and forth about if I want to do this in a video or if I want to talk to my students live about this, because it is verging on a higher level. But I still think it's easy enough for a student to grasp without me being right in front of them. So let's go ahead and review elementary row operations. Now, if you've never heard of elementary row operations, that's okay. This is a topic I teach my intermediate algebra students, and I only do that because I think it's kind of a neat topic, but in linear algebra, it's a required topic. So let's talk about that here. Recall that two systems are equivalent if they have the same solution set. We talked about that in a previous video. So if I say that two linear systems are equivalent, that just means they have the same exact solutions. They may not look the same, and when you graph those systems, they might not graph the same, but where the systems have a solution, those are the same. Those solution sets are the same. The primary tactic to solving a system of linear equations is to algorithmically rewrite the original system as a sequence of equivalent linear systems. Remember, equivalent linear systems have the same solutions. So we basically want to develop an algorithm to modify our current system we've been handed, and in that modification process, we want to create a new system that has the same exact solutions as the previous system. We want to basically keep our solution invariant, is what we'd call that. Each time we create a new system, we want it to be easier to solve than the previous system. And to do this, we need a set of rules to develop an algorithm. What is our set of rules? Well, we call them the elementary row operations. And they're really neat. I love this conversation in an intermediate algebra class because it kind of blows people's minds when you take a very simple example and showcase that, guess what? The solution doesn't change to the system, even if I do these things. So the three elementary row operations, each of which can be performed on a linear system or a matrix. Now that or a matrix, I really don't want you to see that yet, so I'm going to make that disappear. But the three elementary row operations are the following. We're allowed to swap rows in a linear system. That is, if I hand you a linear system, just like this right here. By the way, the solution to this is 1, 1. It's very obvious. If you plug in 1 for x1 and 1 for x sub 2, that solves both of those equations. So that's the solution to this linear system. Anyhow, if we swap rows, that should not modify the solution whatsoever. The solution should remain the same even though I swap those two rows. This is also called row interchanging, depending on the author. So this is the act of exchanging one row for another. The second row operation that will not change the solution to the system is row multiplication, which is called scaling. You're changing the scale of a row. And that's the act of multiplying a row by a non-zero scalar. If, by the way, you don't know what a scalar is a constant. It could be a real number. It could be an imaginary number with a non-zero imaginary part. But the one thing it's not a matrix, and it's not, if you know the word, it's not a vector. So what does that look like here? That just means that if I choose to multiply a row by any number I want, that's non-zero. Let's say I multiply this bottom row by 10. So the way I'd write that is 10 times row 2. That's how I would write that. If I want to modify that row by multiplying it by 10, well, I multiply each component in that row by 10. Now, remember, the solution to the system originally was 1, 1. Do you agree that the solution to this system is still 1, 1? In other words, 1, 1 will satisfy this first equation. And if I plug in 1 and 1 in for x sub 1 and x sub 2 in the second equation, I get a truth statement there as well. So it's not a proof, but it's definitely a really strong justification that scaling a row will not change the solution to your linear system. Now the third elementary row operation, which should not change the solution to your system, is row replacement. This is kind of the most important elementary row operation. They're all important, but this is the one that's really important. I call this the kill step, and you'll see why in a little bit here. But this is the act of adding a multiple of one row to another. So I call this the kill step because you have done this when you've performed the elimination method. Let's just pretend for a moment, since I know that the solution is invariant under scalar multiplication, I will go ahead and just say that that was our original system. Let's just pretend for a second that that was our original system. I am allowed, according to this third elementary row operation, I should be able to add a multiple of one row to another row, and it shouldn't change the overall solution to the system. For example, if I add 10 times row 1, if I add that to row 2, and in fact, normally I would just write it the other way. I'd say, you know what, 10 times row 1 added to row 2. And if I want to make that the new row 2, so I'm adding a scalar multiple of one row to another row to become a new row in that linear system. Well, row 1, x1 minus x2 is equal to 0. That just stays the same. But if you look at 10 times row 1, and if you look at row 2, and if you add those two up, you will get a new equation, which is 20x1. The x sub 2's canceled because it's a positive 10 and a negative 10, and it equals 20. Notice in this case, x sub 1 still is 1. So that solution has not changed. And by the way, when x sub 1 is 1, that means here that if x sub 1 is 1, it forces x sub 2 to be 1 as well. So the solution still hasn't changed within the system. Again, a pretty decent justification as to why that elementary row operation does not change the solution to the system. So again, as I said a few moments ago, solutions to linear systems are invariant or unchanged under elementary row operations. You kind of have to keep those three elementary row operations in mind at all times because you're going to be using them quite often. You can swap rows, you can multiply a row by any non-zero constant, and you can add a multiple of one row to another row. So this is a weird example that I'm about to do, but I like to do this example for my intermediate algebra students because I think that it's just a great example to justify why this works. So we're going to use a system built on x equals 2 to justify why these operations do not change solution sets. So let's suppose somebody walks in the room and they say, I have a system of equations, and my system of equations is just this. It's just x equals 2. It's not really a big system. It's literally a single equation. But you say, I know the solution to that. The solution is x equals 2, of course. Now remember, you can swap rows here, but there's not really rows to swap, so oh well. But let's say that we take, 3 times that row 1 and create a new row 1 from it. So if we do that, we get 3x equals 6. But if you take a look at that equation, well, guess what? The solution is still 2. And guess what? You can take both of those equations, this guy and this guy right here, and you can create a new system from those two equations. And let's suppose that this is our new system, just for giggles here. Remember, the solution set to both of those is the same. They're x equals 2. So that's a solution to this entire system. I am going to add a multiple of one row to another row. And in fact, I'm going to add, you can make up any number you want. I'm going to add 7 times row 1 to row 2 to become the new row 2. Let's see what happens. Well, row 1 doesn't change. But row 2, I'm going to add 7 times row 1, so that'll be 7x equals 14, and I'm going to add that to row 2, 3x equals 6. If you add those up, you'll get the new equation, 10x is equal to 20. What is the solution to that new equation? Well, you guessed it, it's 2. So this is a really good justification. We're saying I've taken an equation I know the solution for, I'm multiplying it by a non-zero constant and the solution is still the same. If I have a system of equations that has that solution x equals 2, and I take a multiple of one of those equations and add it to the new or to the other equation to create a brand new equation, the solution still does not change. What if I were to swap these two rows? What if I were to write 10x equals 20 and x equals 2, and you should know the solution in that system still is 2. So as I'm giving here as a justification, the solution is invariant or unchanged through these 3 elementary row operations. Now obviously this is a trivial example, but let's go ahead and apply elementary row operations to a real problem. And it's kind of silly of me to say a real problem because they're all real exercises, but this is just a larger exercise. How's that? Solve the following system using elementary row operations and showcase the related augmented matrices for each step. So I'm bringing in some of the language we used in the previous video. The first thing I'm going to do is take a look at my system here and make sure that everything's lined up nicely because it just makes the visual very nice. So in other words, I want a column of x sub 1 variables, a column of x sub 2 variables, a column for the x sub 3 variables, and then everything should be in general form, so all the constants should be on the right hand side. It's kind of the first step in solving systems. And I get it if you say, well, why can't I solve that middle equation for x sub 3, for example, and then substitute that into one of the other equations? You can. But the reason why you learn these other methods that I'm showing you right now is because those substitution methods, solving this middle equation for x sub 3, that only really is useful for smaller systems. Real world systems, as I mentioned in a different video, real world systems have hundreds of equations, if not thousands of them, with thousands of variables. So there is not a substitution method that's really going to be very helpful in those situations. So really what I want to do here is I want to do a bunch of steps so that I eventually have an easier to solve linear system. Remember, each step in this process, I want to create a system that's equivalent to the previous linear system. That is, their solutions are the same. And by the time I get to the bottom, or by the time I finish all these steps, it would really be nice if I had some number times this x sub 1 variable plus, let's just say, I'm going to call this a1 for now, and I'm going to call this a2 times x sub 2 plus a sub 3 times x sub 3 is equal to a sub 4. And then I'd like this next row to be b sub 2 x sub 2 plus b sub 3 x sub 3 is equal to b sub 4. And then finally, I'd like the last row to be c sub 3 x sub 3 is equal to c sub 4. Because if we get down to this form right here, which we would call a triangular form, to be honest with you, we can then use back substitution, or back solving, if you will. What you're going to do is just divide both sides by whatever this number is here, and you'll be able to find out what x sub 3 is. And once you find out what x sub 3 is, you can say, great, I know what that is, I'll plug it into this. And now you know the second equation is just a bunch of constants, and there's an x sub 2. And you can solve that second equation for x sub 2, and you would then say, oh, x sub 2 is some other number. I'll say number 1, number 2. And now that you know x sub 3 and x sub 2, you plug them in up there and you get some constant, subtract it from both sides, and then divide by a sub 1, and you should get x sub 1. So the ultimate goal is to get down to a nice, easy, or easier linear system that's in this triangular form, so you could just back solve. But if you look at what we're handed to begin with, this is definitely not in triangular form. So what are you going to do? You're going to use either row swapping or the kill step. And remember, the kill step is when you add a multiple of one row to another row. So that's what I'm going to do here. Let me go ahead and wrap up my triangular form because that's my ultimate goal. I'm going to grab that guy right there, drag him all the way down so that I know where I want to end up. If we do some work, it's going to imply we have a brand new system. The work I want to do here is I want to take, let's see, the kill step. I'm going to take 4 times row 1 and I'm going to add it to row 2 to become the new row 2. Now you might ask yourself, well, why would you do that? And I would respond with, because if you multiplied this by 4, you'd have a negative 4x sub 1. And if you add negative 4x sub 1 to 4x sub 1, they kill each other off. That's why I call it the kill step. And if you use that very same logic, you can create a kill step to kill off this 2x sub 1 in the third row. You're going to take twice row 1 added to row 3 to become the new row 3. So let's go ahead and do that here. Now, normally I would not showcase all my arithmetic in the background, but I do want you to know kind of all the mathematics that's working in the background. So we're going to go ahead in this entire process, by the way, row 1 actually never changes. The only rows that get replaced are rows 2 and 3. I'm going to take 4 times row 1 and I'm going to add it to row 2 to become the new row 2. So my new row 2 is going to be 0x1, so I don't even bother writing that in, 8x sub 2 plus 39x sub 3 is equal to 44 plus 11 is 55. I'll do the same thing for twice row 1 adding to row 3. Twice row 1 is the following. Adding that to row 3, adding those two up, we get the following. So far, so good. Now let me spend a moment writing the augmented matrices off to the side here, just so you can see kind of what's happening. The augmented matrix for the original system was -1, 2, 10, augmented with 11, and the rest of that there. Now, I have to tell you, working with augmented matrices is a lot cleaner than working with the actual linear system. It's only cleaner because you're not having to write the variables and the equal signs every single step. It's just a little bit cleaner like that. The next augmented matrix that we have right here is the following. Now notice that our system is almost, not exactly, but almost triangular in form, which is where we want to end up. We're very, very close. After that single kill step, we used this guy right here to kill everything below it. After that single kill step, we're almost done, but unfortunately, now while this is fine, what we'd like to do is we'd like to use it to kill off that 3. Unfortunately, that's a really weird thing to kill off. So let me look back at our linear system here. Remember, we have 3 elementary row operations. We can swap rows, which I don't recommend doing because you don't want to move this down here or down here because you want to keep it in triangular form. So you'd like to keep this as the only row with an x sub 1 in it. You could swap these 2 rows, but I kind of think that's silly, so don't bother with that either. But remember, beyond row swapping, you can multiply a row by any non-zero constant you want, or you can add a multiple of one row to another. Now I'm going by baby steps here. So I know that I want to somehow kill off that 3x sub 2 in that last row. The way I'm going to do this is use the second row operation, the scaling operation. I'm going to take 8 times row 3 and make that my new row 3. The reason why I'm going to do that is because I'd like those two rows to have something in common. And they both being divisible by 8 is very helpful. So let me go ahead and rewrite that right now. Now I got to tell you, when I did that, I grabbed a calculator for one of my calculations because the numbers get kind of large here. I just made this problem up. That just happens. Okay, not a biggie. You could write the augmented matrix here. I'm actually not going to in this step just because I don't want to. And instead, what I'm going to do is just move one more step and say, I'm going to take, let's see, now I'm going to do this kill step here. So I'm going to take -3 times row 2, add it to row 3 to become my new row 3. Now, just a fair bit of warning here. You will make arithmetic mistakes. That's just it. Like, there's no way around it. I make them all the time. People, it's arithmetic we take for granted. It's like the thing you do daily. And when you do something a lot, you tend to take it for granted. And the arithmetic we do here, it's so simple that we make mistakes. So just be very aware that you can and will likely make little dinky mistakes throughout this process. You do have to check your work in the end to make sure you didn't make a mistake. I am just going to say my mathematics out loud. So let's see, -3 times row 2 plus row 3. So -3 times 8 is -24, then x sub 2, and we're adding it to this 24x sub 2. They kill each other off by design. -3 times 39 is going to be a -117, and then adding back 152 because of this guy, we will get 35 x sub 3. That's probably the part where a lot of people, myself included, will make little arithmetic errors. That's just how it is. The next thing we're going to do is take -3 times this 55. That'll be a -165. And then we are going to add to that 200 to get 35. Now, to be honest with you, me looking at this, I'm very happy with this look right now because I already see that x sub 3 is going to be nice. 35x sub 3 is equal to 35. I immediately know what x sub 3 is. But let's go ahead and write the augmented matrix. And look at that beautiful augmented matrix. That is really what we're aiming for. This coefficient matrix right here is in triangular form. It's triangular form because all the non-zero numbers are above the main diagonal, or they could all be below. But basically we have a bunch of zeros below the main diagonal, or it could be that we have a bunch of zeros above. But in this case, we have a bunch of zeros below, which makes it a triangular coefficient matrix. And we'll see a definition for that later on in the course. Now, finishing the solution here, now that we've gotten down to this triangular form, we just do some back solving. 35x sub 3 is equal to 35 means that x sub 3 is 1. Substituting that into the second equation, we get 8x sub 2 plus 39 is equal to 55. Subtract 39 from both sides, and we get 8x sub 2 is 16, or in other words, that x sub 2 is 2. Taking x sub 2 and x sub 3 and plugging them into the top equation, we get -x sub 1 plus 4 plus 10 is equal to 11. This tells us -x sub 1 is equal to -3, which implies x sub 1 is equal to 3. Check your solutions. I'm saying that because I actually did a little dinky arithmetic mistake in here, and when I went to check my answer, I quickly noticed it was incorrect. Luckily, my dinky arithmetic mistake only happened in one of the last few steps, so it's very easy to correct. However, that's critical that you check your work. Remember, we think the solution is 3, 2, 1. X sub 1 is 3, x sub 2 is 2, x sub 3 is 1. If you verbally check it, -3 plus 4 is 1, plus 10 is 11. That works out there. 4 times 3 is 12, minus 1 is 11. That works out as well. And 2 times 3 is 6, minus 2 is 4, minus 1 more is 3. That works out as well. And there you go. We solved that system using the elementary row operations, and we showed the augmented matrices for each step. Those augmented matrices shown for each step will become very, very important as we move forward. But this is just kind of a higher level review of your intermediate algebra solution style that you did way back when. I hope this was helpful. I know it was very long-winded, but I really sincerely hope that that was helpful for you. All right, I will see you either in class or in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.